Hello students, welcome to lecture 36 of the online course Introduction to Microwave and Optical Metamaterials. Today we will be discussing about brief overview of negative index metamaterials. So here is the lecture outline. We will give you a brief introduction to negative index media. We will discuss about its wave propagation characteristics. So before we come down to negative index medium, we will also discuss double positive medium, single negative medium, okay, and then we will go for double negative medium, that DNG, okay, and finally we will discuss the left hand metamaterials and go for in-depth analysis. So the propagation of an electromagnetic wave through a linear isotropic medium, we have known that it is basically governed by the electric permittivity epsilon and the magnetic permeability mu of the material, right. So in general, these quantities are frequency dependent and they are complex. When you look for wave properties such as propagation constant, velocity, attenuation constant, impedance and dispersion relation, they all can be readily determined from permittivity and permeability. And because they are complex, the sign of the real and the imaginary components of this epsilon and mu, okay, at a given frequency, they basically govern the various regimes of wave propagation. So for media in which you will see mu is real and positive, that indicates that there is neither magnetic absorption nor amplification. The wave property or the wave propagation properties solely depend on the signs of the real and imaginary parts of the permittivity epsilon. Similarly, for media with real and positive epsilon, the magnetic properties which are described by mu, they basically dictate the nature of wave propagation. So when you have magnetic media, that includes media with metal components that carry induced electric currents and can generate magnetic fields, they generally have complex values of mu with real and imaginary parts that may be either positive or negative. So in most general cases, the manner in which the signs of the real and the imaginary components of epsilon and mu, they basically dictate the characteristics of the wave propagation in a more subtle way. So let us now look into the single and the double negative media, okay. So here you see the axis, the coordinate shows that you have epsilon on the horizontal axis and mu on the vertical axis. This is the origin, so this part is positive for epsilon, this is positive for mu, this is negative for epsilon, this is negative for mu, right. So we are basically considering single negative materials, so where either epsilon or mu is negative. So which are those two regions? These are basically this and this quadrants, okay, the second and the fourth quadrant, this one and this one. So these materials are basically opaque, but they support optical surface waves at boundaries with double positive material, which are basically the common transparent dielectrics, okay, the first quadrant materials, okay. So here when you consider single negative materials, you can name a few, something like metal such as gold or silver, they exhibit negative permittivity while maintaining a positive permeability, right, in the infrared and optical ranges, okay. So that is where you get the normal materials, single negative materials. Now when you come here, okay, this one also has got single negative material, but this basically shows that your permittivity is positive, permeability is negative. So this is basically magnetic plasma, but no naturally occurring material at optical frequencies or wavelength shows this kind of characteristics. Next we have this third quadrant, which is particularly interesting because you have DNG materials here. DNG means double negative metamaterial, where both permittivity and permeability are negative. So, these materials are also called left-handed media, and they are transparent. Transparent means they allow wave propagation, and they have refractive index, but they have negative refractive index. So, they can satisfy the application of Snell's law at a double positive and a double negative interface that will give you negative angle of refraction, right. So, the implication of this property for materials with these multiple boundaries are most interesting, and you can make metamaterials that can exhibit such amazing properties in your desired frequency band. So, let us first confine ourselves to the lossless and the passive media, in which there is neither absorption nor gain, okay, indicating that we are basically away from the dielectric and magnetic resonance. So, under this kind of circumstances, you can see that both epsilon and mu are basically real, and their signs can be either positive or negative at a given frequency, right. If you consider double positive metamaterials, you are basically considering that both epsilon and mu are positive. So, these are the materials which are basically transparent, that means they allow light to propagate, right, and they have positive refractive index. So, all the ordinary dielectric media, they basically fall in this category, that is in the first quadrant. So, you can also see the E and the H axis, this is the K, okay, there is the wave vector, and also you can see there is a wave propagation shown here with the pointing vector of the wave in the same direction of K. Okay. Now, that is something you need to understand, that for the third quadrant, that is for the double negative metamaterials, something is different here. You have E and H, but you have K pointing in the other direction, whereas the pointing vector goes in the same direction. Okay, we will come to that. So, let us consider the wave propagation characteristics. So, for simplicity, we can consider a monochromatic plane wave with electric and magnetic complex amplitude vectors, which are given by E r, that you can write as E naught exponential minus j k dot r, and you can have magnetic field also in the same form. So, here k is basically the wave vector. So, Maxwell's equation can then be written in this form, that k cross h naught will be equal to minus omega epsilon E naught, and k cross E naught will be nothing but omega mu h naught. Okay. So, this first equation basically indicates that your E naught is orthogonal to both k and h naught, while your second equation indicates that h naught is orthogonal to both k and E naught, right. So, that means these three vectors E, H and k, they are basically forming a mutually orthogonal set. Now, the fixed orthogonal directions, okay, if you choose for the fields E naught and H naught, then the wave vector k is just orthogonal to the plane that is defined by those two vectors, right. And you can actually see that the actual direction basically will depend on the signs of epsilon and mu, okay, which we will observe shortly. Okay. Here also you can get some idea that the associated wave number, which is nothing but the magnitude of the wave vector, that comes from k equals omega square root of mu and epsilon. So, the value or the sign of this mu and epsilon plays an important role. Another important parameter is impedance, which is basically the ratio of the magnitudes of the electric and the magnetic field. Okay. So, that you can define as eta, that is omega mu divided by k, which is nothing but square root of mu by epsilon. Okay. So, these two things play a very important role, and since we have understood that k, wave vector or wave number, is generally a complex quantity, you can always write it as beta minus j gamma, where both beta and gamma are considered to be real, okay, and you can write beta minus j gamma will be equal to omega square root of mu epsilon. Now, what is this beta? Beta is basically called the propagation constant, which is nothing but omega by c. So, that basically determines both the wave velocity, that is c equals c naught by n. C naught is the vacuum speed of light or speed of light in vacuum, and divided by n is basically the wave velocity in a refractive index of n, that is the medium, right. So, another term remains here, which is gamma, that is basically giving you the field attenuation coefficient. So, now consider the implications of these equations for media in which you have both epsilon and mu to be real, but they can be either positive or both may be negative. So, let us consider the first case, which is a double positive medium, that is where both epsilon and mu are positive. So, as we have discussed briefly there in the previous slide, that if you have E and H which are orthogonal to each other, K is also orthogonal to them. Okay. So, you can see that the plane wave propagating in an ordinary double positive medium looks like this, where S shows the Poynting vector, that is the flow of energy also happening in the same direction of K. So, what you can understand from here, these are basically the phase front, okay, plane wave. So, it looks like this, okay, and you can also see that E, H and K are basically forming a right handed set, okay, and the wave front basically travels in the same direction of the power flow. So, that is your double positive medium, okay. So, this basically provides a simple and familiar benchmark. So, here both epsilon and mu are positive, so that you also get K, that is the wave number, and eta, the impedance, they are also real, and here gamma is 0 because that is the attenuation coefficient and the imaginary part, okay. So, that goes to 0. Beta is simply can be written as n k naught. N is nothing but square root of epsilon mu divided by epsilon naught mu naught, and eta, that is the impedance of this medium, can be given by square root of mu by epsilon. So, we understood that to support transverse electromagnetic wave for which the vectors E or E naught, H naught and K should be also, they should be all mutually orthogonal. So, that is the case for TEM, transverse electromagnetic wave, and they basically form a right handed system, okay. So, we also discussed about the power flow. So, that is basically coming from the Poynting vector S. So, you can calculate the Poynting vector as half E naught cross product with H naught conjugate, okay. So, if you calculate this, that basically points in the same direction of the wave vector K, okay, and the intensity of the wave, that is basically the power flow per unit area, will be given as I, which is nothing but the real part of the Poynting vector S, and that can be calculated as modulus of E naught square, that is modulus of the electric field square, that is the electric field magnitude square divided by 2 eta. Okay. Now, let us look into that is the simplest medium, that is the double positive medium, which we encounter very closely every day because these are the ordinary dielectric medium. Now, we move on to the other type, which is single negative medium. So, in single medium, negative medium, as you understand, either epsilon or mu can be negative. So, that will make your K and eta both imaginary, okay, because you will also get gamma, that is having equation of omega square root of modulus of epsilon times modulus of mu. Beta will be 0, that means there is no wave propagation allowed in these cases, okay, it will only attenuate, and then n can be obtained as j square root of modulus of mu divided by modulus of epsilon. So, these parameters basically correspond to a exponentially decaying field that basically behaves as exponential minus gamma z, where z is basically the propagation constant. So, this attenuation constant tells you that the wave is basically going to exponentially decay in this kind of single negative medium. And obviously, as I told that beta is 0 here, that means the single negative medium does not support any propagation waves. Because the wave is attenuated in this kind of medium, the optical intensity, you can see that it will get attenuated by a factor of 1 by E at a depth of dp, which is given by 1 by 2 gamma. That can be written as lambda naught divided by 4 pi square root of modulus epsilon by epsilon naught into modulus mu by mu naught. So, here dp is basically called the penetration depth or the skin depth. Now, the imaginary impedance eta also indicates something that tells you that there is basically a pi by 2 phase shift between the electric and the magnetic fields. And another important factor is what is happening to the energy flow. We already got an understanding that beta is 0, so wave does not propagate. So, even if you calculate the Poynting vector as S, okay, which is half E naught cross product with H naught conjugate, will come out to be imaginary. That means, if you find out the intensity, which is basically the real part of the Poynting vector, that will come out to be 0. That means, there is no power being transported through such a medium. Now, we go to the third quadrant, which is basically the double negative medium D and G. So, in this medium both epsilon and mu are basically negative. So, you get k, the wave vector or the wave number, the amplitude, is given as omega square root of modulus epsilon into modulus mu, right. So, this is real, okay. And then in this medium, because both are negative, you get a real quantity, but then you get a negative sign along with that. So, what you also obtain, you can also see that gamma, the attenuation constant will come out to be 0 because it is a real quantity, and beta is n k naught, where n can be written as minus square root of modulus epsilon by epsilon naught modulus mu by mu naught. So, you are getting a negative refractive index and you are getting an impedance that is given by square root of modulus mu by modulus epsilon. So, what you obtain here, as I mentioned, that you are getting the refractive index to be negative, and more importantly the medium has got 0 attenuation. That means, the medium can sustain propagation of wave without any attenuation. Now, if you look into the sign of the square roots, okay, you can understand that the direction of the vector E naught, H naught and k must be determined directly from the Maxwell's equation. So, if you go back to the Maxwell's equation, the previous ones, and here you write it specifically for the double negative material, you will write k cross H naught will be mu modulus of epsilon E naught, okay, and then you have k cross E naught, that will be minus omega modulus mu H naught, okay. So, you are basically replacing from the double positive media if you compare. So, this epsilon is now replaced as modulus of epsilon, this mu is also replaced as modulus of mu, okay. So, because of that, what you are also obtaining is nothing but a sign reversal, okay. So, this basically tells you that there is an exchange in the role of the electric and the magnetic field, okay, between the D and G double negative and the double positive medium. So, how do you interpret it? Okay. So, you can see that in the double positive medium, okay, these are not the double positive medium, okay. So, in normally the double positive medium, we have seen that E naught, H naught and k, they basically form a right handed set. So, in the double negative medium, they will basically form a left handed set. So, if you do E cross H, okay, you have to use the left hand. So, your k vector will be along this direction, right, but your energy flow will be in the earlier direction. So, you can actually follow this one, or if you try to interpret this figure. So, here what we are doing that E and H, so E field is basically now exchanged with H, that is what that equations gave us, right. So, the E and H get swapped. So, here also you can see E cross H is basically giving you this kind of k vector. So, again you can use the left handed rule and you can find the k vector to be here if the E field is in this direction, right. So, the wavefront basically travels in the opposite direction of the power flow in either cases. Okay. These are the two orientations that you can see. So, these two things are basically identical representation, just that this is 90-degree rotated with respect to this one, right. So, what is important here to notice that the impedance eta is positive, the wave number, that is k, is taken to be negative, and you also get the refractive index to be negative, and that is why this DNG medium, that is double negative medium, is called negative index metamaterial. So, now let us do an in-depth analysis of this, that what happens when both mu and epsilon are negative. So, we first of all we understood from the Maxwell's equation that when you put mu and epsilon both are negative, that signs can be adjusted into the fields, okay, and that will basically change your system from a right hand system to a left hand system. Okay. So, you are basically getting E, H and K to form a left handed system. So, that is basically coming from this. So, this is the right hand system, this is the left hand system. So, let us discuss the overall picture of this. So, let us first look into the complex wave vector plane. Okay. So, here this is the complex wave vector for electromagnetic waves in different types of materials. So, we will be distinguishing the right handed and the left handed materials. So, we have plotted the two axes. The real part of the k comes in the horizontal axis, that is the real part of the wave vector that corresponds to wave propagation. Imaginary of k is in the vertical axis, that is the imaginary part of the wave vector that basically corresponds to wave attenuation. If that is positive, if it is negative, it gives you growth. Now, we can define right hand material, which is basically located on the positive real of k axis. Okay. It is characterized by both permittivity and permeability being both positive, right. So, here the wave can propagate normally, that means the phase velocity and the energy flow will be in the same direction. Now, comes the other case, that is of left hand materials. So, that is located on the negative real part of k axis, right. So, here it is characterized by both positive both permittivity and permeability becoming negative. So, here also wave can propagate, but it propagates with a negative refractive index, that means the phase velocity and the energy flow are basically opposite to each other. So, in both cases you can see you are having propagation along the horizontal direction, right. So, here both permittivity and permeability are having same sign. So, here both are positive, here both are negative. So, when both are positive you have right hand material, when both are negative you have left hand material. Now, there are also evanescent waves which are in the vertical direction, as you can see here. So, when the permittivity and permeability have opposite signs, you are basically having evanescent waves. The wave will decay if the imaginary k is positive, and the wave will grow exponentially if the imaginary k is negative. Okay? And in both the cases propagation is not allowed. So, propagation, just the final summary is that the propagation is allowed along this horizontal direction that happens when both permittivity and permeability are of the same sign. So, if both positive you get right handed, both negative you get left handed. Evanescent waves are along this vertical direction when permittivity and permeability are having opposite signs. The wave either decays or grows, okay, depending on the sign of the imaginary part of k, and there is no true propagation here. So, this is the condition that epsilon prime, that is the real part of permittivity, and mu double prime, that is the imaginary part of the permeability, plus epsilon double prime and mu prime, if this is positive, that means it gives you right handed propagation, that means energy propagates in the expected direction. And on the other hand, if you have this term becoming negative, you are getting left-handed propagation, which indicates negative index and a reversed phase velocity. So, with that we conclude this lecture. If you have got any query regarding this lecture, you can drop an email to this email address mentioning the course name and the lecture number on the subject line. Thank you.